Thank you for joining us for this broadcast of Science and the Solar Eclipse. I'm your host, Gordon Dickson. Dr. George Matzko is a research chemist and professor, and he has agreed to join us to talk about what we have learned about solar eclipses. Throughout history, it has been during solar eclipses that we have learned so much about the sun and the stars, about starlight, and about the nature of the universe. Now let's join Dr. Matzko. Thank you again for joining us today. We're talking to Dr. George Matzko, and one of the reasons that we are talking to him is we have a number of solar eclipses coming up in the next few years here, various places on Earth, and we wanted to get a better understanding in these broadcasts of exactly how a solar eclipse has helped us to understand the sun and, as we'll discuss, even the nature of light and how light travels to us. So, Dr. Matzko, thank you again for joining us on the broadcast today.
Thank you very much.
Last time we were talking a little bit about solar wind and how it's evident in the northern lights. And so let's pick up our discussion there if we could and understand a little bit more about what's happening on the electromagnetic spectrum as it's coming to us from the sun.
So the solar wind is a stream of charged particles, mainly protons and electrons. So it's not really electromagnetism in that sense. Okay, if we're talking about gamma rays, that's electromagnetism. But it comes from the sun's outer atmosphere, known as the corona, and flows out into space. And it continuously flows and permeates the entire solar system. Solar wind is primarily driven by the sun's high temperature and the escape of particles from the sun's gravitational pull. And it can travel between 300 and 800 kilometers per second and carries some of the magnetic fields that originate from the sun. So you may have heard that there's some people that are interested in sending astronauts to Mars. I think Elon Musk had a sign-up list for teenagers, where like 1,500 teenagers signed up for a one-way trip to Mars. But part of the problem with that is that if you go out into outer space, there's no longer a magnetic field to protect us from the solar wind. We call that the magnetosphere. And that's where we get the auroras, the northern, southern lights and magnetic substorms and so forth. And so we really wonder what would happen to astronauts in the space between the Earth and Mars. Mars doesn't have a magnetic field. God created a magnetic field to protect the Earth, but there's nothing on Mars to protect them. My personal theory is that those particles, the solar wind, would actually destroy the gut bacteria in the astronauts, and the astronauts would literally starve to death because they couldn't get nutrition from their food. So that's my guess. If it ever happens, we'll see if I'm right about that.
And one of the first questions that comes to my mind when I hear that is, so think about Skylab and the International Space Station. Have they seen any indications of that? Have they done any experiments on that very issue in orbital work?
Yes, so the space station gets some protection from the Earth's magnetic field. We're talking about in the regions beyond that.
I see.
Even then, in the space station, we can see many, many changes in the genetics of the people who are there. I can't remember right offhand. Maybe you remember the name of the twins. They sent one in to the space station.
Yes, I do remember that.
Mark.
One of them ran for office in Arizona. I remember this.
That's right.
Yeah.
Mark Kelly.
Yeah.
And I can't remember his brother's name. So one stayed on Earth in Arizona, and the other went to the space station. And so the number of changes in his genetic material is just huge. Now, the God has designed our bodies to be able to repair a lot of that, but some of these were unrepairable. And, hundreds of changes that were unrepairable. And he's within, the protection of the Earth's magnetic field there in the space station. What's going to happen to people that are, beyond, say, the orbit of the moon or on Mars?
And this is different, if I'm understanding you correctly. This is different from, like the gamma rays and things like that and the dangers implicit in those that you talked about in a previous broadcast.
That's right. So that's electromagnetism. Gamma rays are a type of light that we can't see. and they're absorbed by the atmosphere. So you're getting more gamma rays up there as well. But we're talking more about charged particles, that are streaming through space that are affected by magnetic fields. That's what we're talking about here.
It's really fascinating when you think about this. We're talking about it in terms of a solar eclipse. I mentioned in an earlier broadcast, if you walk out and tell somebody, hey, the sun is shining, everybody says, okay, hey, so the sun is shining. But wow, let some event like a solar eclipse come along, and suddenly everybody's fascinated with the sun. And you and I have been talking about the chemistry of the sun in earlier broadcast and just how it all works together. That is really, really fascinating to think about.
The Bible tells us the earth is given to the children of men. I mean, God designed this planet for life, and so life could survive, thrive on this planet. But the rest of the universe, he hasn't given to us to live in. And we'd actually have more chance of living on the moon, because at least we could maybe bury ourselves down in one of those lava tubes in the moon and protect ourselves. But Mars is a very hostile environment. There's no magnetic field. There is the soil has lots of perchlorates, which is like rocket fuel. Doesn't mix well with biological organisms. It's very, very cold. There's very little atmosphere there, very little oxygen. Plus the tilt of Mars. Our Earth is tilted. The moon actually controls the tilt of the Earth. And it keeps it steady at 23.5 degrees. But Mars doesn't have a big moon like we have. And so its tilt varies from 0 to 60 degrees. Wow. You can't live on a planet like that. Elon Musk may not have figured this out, but you can't live on a planet like Mars.
So all the teenagers who may be thinking about signing up, we recommend you think again about...
don't do that.
Don't do that.
Lose a lot of teenagers that way.
Now, how is light different from, say sound? How are light and sound different?
So sound is transmitted through a medium. It's compressions and rarefactions, we call it. It squeezes together and gets further apart. And so it travels, it's not a transverse wave like light is. And because it depends on depends on the medium. In other words, more than light would. Okay. So light travels much faster than sound, and a vacuum light travels at about 186,000 miles per second, or about 300,000 kilometers per second. Mm-hmm. That's 671 million miles per hour. Okay. Now sound's much, much slower because it depends on the medium. And it depends, I can't tell exactly what the speed of sound is because it depends on the humidity or, the temperature, that type of thing. Mm-hmm. But basically 343 meters per second at room temperature, that's about 1 mile every 4.69 seconds. Okay. And it's going to depend on the temperature and humidity of the air that is traveling through. You may have seen, those old westerns where the Indian comes to the railroad track, and the iron horses on it, and he puts his ear to the railroad track, mm-hmm. and he can hear the train coming. Mm-hmm. Well, that makes sense because the sound travels a lot faster through a denser medium like iron, and so you can hear the railroad train coming faster through the track than you can through the air.
Now, I remember when I was a child, one time there was a lightning strike, and my father began to count in seconds, and he basically taking advantage of the difference between those two speeds, between light and sound.
That's right.
So how a lightning strike, say, I remember reading that lightning heats the temperature of the air around the strike to above the temperature of the sun, or something like that.
About the same as it's above the temperature of the outside of the sun, the photosphere of the sun, and not the core of the sun, but the photosphere of the sun. So it heats the air so quickly. So what you have, in Job, it talks. There's a little bit of scientific foreknowledge there, where in Job, God talks about how he's made a way for the lightning.
Mm-hmm.
And we didn't understand that until recent years, where there's actually a way for the lightning. We call it a lightning leader or lightning channel.
Mm-hmm.
And so when the lightning channel comes down, it follows paths that are opened up by ionizing radiation from outer space, could be from different galaxies and so forth, that are zipping through the atmosphere. And this lightning leader, it's about a half inch wide, comes down, and then it connects to the Earth. And then what we actually see is the return stroke. So the lightning leader is traveling at about 60 miles per second. The return stroke travels at 60,000 miles per second. And so we don't have any cameras that can capture that motion. It's too fast for us. But we can see the lightning leaders that it talks about in the book of Job. So that's instantaneous as far as we're concerned. The light's traveling to us instantaneously. The thunder is just that air that's being expanded by the heat, and it's expanded faster than the speed of sound. And so we get a shock wave. It's like an airplane going faster than the speed of sound, getting a shock wave. And so that's what we're hearing. That thunder is a shock wave of the expansion of the air faster than the speed of sound. And that's traveling to us about 1 mile every 4 or 5 seconds. So your father was probably counting 4 seconds or 5 seconds to see how many miles away the lightning was.
Yeah, that's exactly what he was doing. Yeah, and that's one of the ways we learned to tell, especially growing up in Northwest Florida, out on the sandy beaches and things like that. We learned to tell how far away that strike was by doing it that way. We got a couple minutes left here in this broadcast, but the idea of plasma, could you describe to us plasma? I remember reading that it's formed in, I'm not sure if formed is the right word for it, in lightning, but it also exists in the sun. Am I thinking correctly there?
Yeah, so the temperatures are so high that it just strips the electrons off the atoms. So atoms have, in the nucleus, they have protons and neutrons, and in the outside of that, we have the electrons. And so there's so much energy there that it rips the electrons off. And so now we have, sort of bare nuclei that exist in the sun, and with the electrons stripped off. So that's a plasma. So we have a little plasma ball we use in our demonstrations. And I have one that's red, which is neon, and one that's blue, kind of a bluish, purplish color, that's argon, and a greenish one that's krypton from these noble gases. And we can generate enough voltage to strip the electrons off these molecules, and they glow. They glow when we do that. The plasma in those plasma balls glows that way. So it's not just in the lightning or the sun. We can actually do it in our little plasma balls.
So does that mean it's a fourth state of matter? If I'm understanding correctly, like you have solid and gas and liquid. Is plasma, does that fit in one of those categories?
Yeah, some people would call it a fourth state of matter. I guess it's just a matter of what you count. It's so different from its normal state when it has electrons around it. It's kind of hard to, as a chemist, to think of it that way. Chemists don't usually work with plasmas. We work with, molecules that are a little bit calmer than that.
Yeah. Well, we have really enjoyed talking again to Dr. George Matzko as we are anticipating a solar eclipse here in 2024 and several others across the next several years. It really has been a pleasure to talk to you again today. So, Dr. Matzko, thank you for joining us.
Thank you for inviting me.
These broadcasts are brought to you by LiveServeLead.com. Live, Serve, Lead, helping others succeed.